Hello and welcome to 2017 AP Chemistry FRQ 7's walkthrough. Today we're going to be looking at this question, which starts with the electron spectroscopy represented above and tells us with question A to identify the element. First things first, whenever we look at this, we want to look at the binding energy, find out where the high end and low end is. High end's over here, low end's over here. So wherever the high end is where we start our labeling. This is going to be our 1s orbital. The next low peak is going to be our 2s. And the next peak after that is going to be our 2p, and so on and so forth through our filling order. The question is, how many electrons are in each level? In order to move past a level, you need to fill this up. So the first one needs to have 1s2, because if you go to 2s, you need to have filled 1s. Again, same logic, 2s needs to be filled to go on to 2p. Now, 2p is where the trick is. Because we don't know where exactly it is, and these are only relative numbers of electrons, we need to scale it up. In this case, 2 electrons takes us 2 steps up, so three steps up, 1, 2, 3, would be 3 electrons. This would be 2p3. And that's how you have to do these, okay? Start with one end and go, okay, which one's this? How many electrons does it have? And then based off that scale, whatever this is, if this is 1, 2, 3 high, however, you can figure out every other scale in there. Then the question is, what element has configuration 1s2, 2s2, 2p3? So we come over to our handy dandy periodic table, we go 1s, 2, 2s, 1, 2, 2p, 1, 2, 3. Tells me that it's nitrogen. So the element is N, or nitrogen. Done. B tells us to calculate the K value for a radioactive isotope of the element that decays with a half-life of 10 minutes. Calculate the rate constant K for the radioactive decay. Include units with your answer. Okay. There is only one equation for half-life that involves time and K, and that is K equals 0.693 over T1 half. We have T1 half, we don't have K, we're looking for it, so K equals 0.693 over 10, and then we're going to put our units here, minutes. Continue on. This will give us 0.069. We stop there because 6.93 divided by 10, which is only 2 sig figs, means we only go to 2 sig figs. But what about our units? Well, it's in minutes originally. Now it's 1 over minutes. So it's minutes to the minus 1. Or min 1 over minutes, whatever. But that's super simple, super easy. C is probably the hardest part of this problem, but even that's super easy. It says, if 64 atoms of the radioactive isotope were originally present in a sample, what is the expected amount of time that will pass until only 1 atom of the isotope remains? Show how you arrived at your answer. There are 2 ways to go about this. There's the quick and easy way, or there is the slightly more drawn out way, but both are very simple. If I start with 64, I have it, I go to 32. I have it again, I go to 16. I have it again, I go to 8. Have it until I get to 1. Then I count how many steps that is. That is 1, 2, 3, 4, 5, 6 steps, or 6 half-lives. If each half-life takes 10 minutes, 6 half-lives times 10 min per half-life gives me 60 minutes. Done. Or if you'd prefer, you can go, okay, well, we have an equation for this. This is a first order reaction, which tells me that this equation here is true. Ln of A naught minus ln of AT minus ln A naught equals negative KT. We need to solve for T. We have everything else. ln of A is 1. ln of A naught is 64. And K is the value we calculated here, negative 0.069 T. If I solve it for T and do all my math very, very carefully, I will get, once again, 60 minutes. I personally prefer the first step because it doesn't involve as much logarithm math, but either way works. And that is 2018 AP Chemistry FRQ number 7. Thanks for tuning in. Have a good day.